Hey everybody, today we're going to be reviewing AP Calculus Unit 5 on the analytical applications of differentiation. So let me first explain what that means. So the last unit was the contextual applications. That's more of the real world examples, like related rates is kind of more real world. The linearization ones, that's, approximations are used heavily in the real world. But here we're talking about the more analytical approach of calculus, and really what that is really not so real world, but instead it's going to be more of like looking at the behavior of the derivative and the functions and all that kind of stuff, and kind of just like really like looking at them in depth. And really I'll show you what that means. So first, let's just dive into it. We got the 4 key theorems of derivatives, really of calculus in general. There are a lot more theorems, but these are the 4 that we're going to focus on today. So let me just step out of the way. So first we got the mean value theorem. Let me actually show you some of the abbreviations. So you'll often see this as MVT, mean value theorem. Then we got the Rolle's theorem. This doesn't really have any sort of abbreviation. But then we have the intermediate value theorem. This is typically IVT. Right, that's a common way you'll see that. And then we have the extreme value theorem, EVT. And these names should make sense once I discuss them. But yeah, so again, the goal of this series is to really just kind of give you the explanations behind everything and not really work through a lot of problems. It was really hard to avoid that for the last unit because of how real world it is. But yeah, here we're not really gonna walk through so many problems. I'm just gonna like talk about what each of them mean and give you a really deep understanding, because a lot of calculus teachers don't really give you the deep understanding that you really deserve, that you need. But that's what my goal is here. So the first one is the mean value theorem. What does this mean? Well, basically what it's saying is if you have a function here, let's say we want to compare 2 points. So let me take this blue here. Let me just say we have a point here, and then we have another point. Actually, I don't want to do it there. No, that's not a good idea. Hold on. Because I want to make it, you'll see why in a second. Hold on. So, yeah, okay. So let's say we have a point, I don't know, here. And then let's say we have another point up here. And I'm going to connect that with a line, and I'll just do a dotted line. Hopefully you can see that. So really that's a straight line. And what this is a secant line. If I just extend it this way and this way, this is a secant line. It's not the straightest line in the world, but you get what it's supposed to be. So this is a secant line. And if I draw a tangent line at a particular point, and I'm going to put it here for a specific reason, and if I basically make it just kind of extend off into both directions, you kind of notice how these lines are parallel, right? Kind of. In my picture, they're not too parallel, but they're supposed to be parallel. And you're like, okay, well that's cool. It just happens to be that way, right? Well, not necessarily. This is actually always going to happen. If you have a function it has to be, okay, actually, let me get into the specifics in a second. But if we have this function here, and we pick 2 points, right, for some interval, and we want to draw a secant line through that, so the average rate of change of the function, this is your average rate of change over that interval, it's going to be equal to the derivative, the slope of the tangent line at a particular point in between that, inside that interval. So what that means, so basically if I just give you all the details now, f has to be, so let me say f, the function f, is continuous and differentiable. So first let me explain the continuity part, so I'm going to just call it C. C for continuous. It has to be continuous because if it wasn't continuous, you could move like any of these pieces anywhere, and it wouldn't really work. You can kind of like look at that for yourself, but if you made this part like just stop there and then like it picks back up here and then just keeps going, it doesn't really work out. So you know. But you also have to be differentiable. So let me put a plus D here. You have to be continuous and differentiable. Obviously, you have to be differentiable. Why? Because you're taking a derivative. You have to be able to, your function has to be differentiable in order to take your derivative. And of course, this is going to be on the closed interval between these two functions. Well, let me specify more. You're going to be continuous on that closed interval, but you cannot be differentiable on the closed interval. You can only be differentiable on an open interval. And that's always the case. Your function can never be differentiable on a closed interval. Because, and this kind of goes into a little more like deep analysis, so you don't really have to know for the AP exam, but it's kind of good to know. Let's see, so if I just have some interval on the real number line here, so this is the real number line, so we just put the R. So for a derivative to exist, remember the whole derivative limit definition with the x plus h's and all that kind of stuff. That h is a small difference, right? So pretend that h first is some actual finite difference, like 0.5 or something. Okay, so let's say we're looking at let's assume that we could be differentiable on a closed interval. So let's say we're talking about the like on the endpoints. I mean, let's say we're trying to find the derivative at this particular point, right? So that means that we need to find some h, right? And let's say our h is like over here, right? Or well, so this is our x, that point there, and this is our x plus h, right? And then this h, as it goes to 0, this difference is going to go to 0, and this point is going to go right there, right? But remember, a limit isn't exactly the same as being that point. You're approaching that point. That's the whole concept of limits. And so since you're approaching it, you'll never actually get to that point. So you're going to hang just outside that interval. And that should be like, okay, well, if you're outside the interval, then it shouldn't really count, right? Well, yeah, exactly, it won't count. It's not like that point, that particular point is not differentiable. Well, maybe your h was over here, right? Okay, well that would work, but really you should think of like a neighborhood around this point, like a kind of like a little ball. Those are two actual terms that are used in analysis and topology, if you know that. So you should think of this ball with a radius h, and it's going to 0. The radius is going to 0, and you have to your ball has to be entirely inside of this radius of this open interval to make this point differentiable. So I hope that kind of makes sense. You just have to be inside of that interval. Now, what's the difference between this and some open interval? So if instead, let me just erase this whole thing. So if instead we had some open interval, again, on the real number line, so real, if we had, so of course you can't actually have some point on the curve, right, or on the endpoint, because there is no endpoint. So I can't draw it exactly on it. I have to draw it like right next to it, right? So this ball, remember, this ball can be super small. The ball cannot actually be 0. That was our problem originally, right, with our closed interval. Here, the ball can be like super small. Even if our point is like right next to the like the closed or the open interval thing, our ball can be smaller than that, because between any two real numbers is another real number. Like, there is no smallest real number, so we can go as small as we want. And so I drew like a small ball there. I don't know if you can see it, but yeah, this ball actually works in this case. And so that's kind of why it just really has to do with like infinities and like really small infinitesimals and all that. But yeah, I really talked about that a lot. Probably shouldn't have gone into so much depth because I don't want to confuse you guys. But that's kind of the whole reason why you cannot be differentiable on a closed interval. Well, actually, you can be differentiable on the open interval, just not the endpoints. So that's why it's not a closed interval. Okay, so for the mean value theorem, back to this, you have to be continuous and differentiable, continuous on the closed, differentiable on the open. And this is going to mean, so let's actually call these points, let's label these points. We'll call this x value A, we'll call this one B, and then we'll call this one C. So A, B, and C, all right? Those are our x values. So we're going to say that f of A, or let me do f of B minus f of A over B minus A equals f prime of C, f prime of C for some C. Okay, so this is a capital C, this is a lowercase c. So the average rate of change, this is just our slope formula, is equal to the derivative at a particular point C for just some C, right? I just put this for clarity, okay? So that's the mean value theorem. The Rolle's theorem is actually very similar to this. You just, again, f has to be continuous and differentiable. But there's another added condition. So if we have our A here, so let me actually draw it with blue again. So if we have our A here and our B here, okay, so let me draw the tangent line. Let me make the tangent line actually connect them. Okay, close enough. So you can notice that f of A is actually equal to f of B. They're on the same y-axis, so they have a horizontal tangent line. So the slope of the tangent line is 0, okay? This is crucial. So also, I'm going to note that f of A equals f of B. Okay, so this means that the slope of the tangent line is 0. So at some point, your derivative is going to be 0. So at this point here, the slope of the tangent line is 0. I'm sorry, I think I called this a tangent line. I meant that this is a secant line. This is our tangent line. This is not a great tangent line. Hold on, let me make that a little better. Alright, it's still not perfect, but it's better. But yeah, so this tells us, actually let me put the implication arrow. So that implies that, just so it's clear. So then this implies, right, that's what that arrow means, it implies. This is kind of an if-then statement, if this, then that. So if this, then this, right? Okay, this implies that let's see, the derivative, so again, let me label these. So this x value is A, this is B, and this is C, okay? This implies that f prime of C equals 0 for some C. And assuming that you're comfortable with the mean value theorem, which again, you shouldn't be too comfortable with it now, like I gave you the explanation, but you should still definitely work through some problems. You can look at some AP Calc, past exams and stuff like that for some practice. But here, I'm saying that the derivative should equal 0 for some C, and if you're good with this should come naturally. What I'm saying is that, again, the slope of the tangent line, or the slope of the secant line is 0. So that means our slope of the tangent line is 0, because this average rate of change is 0. We're just substituting 0 in for this entire thing. So this should come naturally, right? F prime of C equals 0 for some C. We're just substituting 0 for this, and that's really it. That's what Rolle's theorem is. It's really just a corollary of the mean value theorem. A corollary is kind of like a follow-up, basically like a follow-up theorem, like a sub-theorem. But yeah, so these are the first two. Now let's move on to the next two. So we have the intermediate value theorem. Really what this is you really just can't skip any y values on an interval. So basically, if I have, let's see, if I have points here and here, I mean, it doesn't matter. If our function is continuous, then we're not going to be able to skip any y values. So what that means, so f is continuous. This implies that each x value is going to have like a corresponding y value. Yeah, or is it the other way around? Hold on. So let's see. So f of hold on. So f of y. Yeah, f of y exists for all y on a comma b. So if this x value is a and this x value is b, all we need is for our function to be continuous, and then f of y is going to exist for all values of y on this interval. This is an interval of x. So what I'm saying is that if we're continuous, that means all of our x values exist there, right, on the interval. So if all of our x values exist, all of our y values have to exist. And that's going to be important because they might ask you questions like what value of this, of like c, for example, would satisfy this, and you need to make sure that all the y values are filled in so that your function actually satisfies the intermediate value theorem. So all you need is for your function to be continuous, and you'll be good with this. Alright, last one, the extreme value theorem. This has a cool name because it's extreme, okay? So really what this is, let's see, I think you just need it to be continuous. Let me double check actually. Yeah, so all you need is for f to be continuous, and I haven't told you what it is yet, but all you need is for f to be continuous. So this is another easy one. These two are pretty, they don't have a lot of what's the word, like requirements. But yeah, so let's see, so all you need is your function to be continuous, and really what this says is that there's going to exist an absolute minimum and an absolute maximum on some closed interval. So basically, if we have our a here and our b here, oops, I meant to put the, hold on, the b is here. So if we have a closed interval here, that means from this point to this point on the graph, we're going to have somewhere, we're going to have an absolute minimum and an absolute maximum. So remember, absolute maximum occurs where you have a local maximum, or it could also possibly occur at the endpoints of the interval. Absolute minima, that's the plural, they can occur at local minima or at endpoints. You can only have one of each. Or you can have zero if you're not on a closed interval. Here, it's saying if you are on a closed interval and you're continuous on that closed interval, obviously you have to be continuous, you're going to have some point somewhere where you have an absolute minimum and max. So in this case, our absolute minimum is going to occur on this endpoint, right? Because, so this is the endpoint of the interval, so we kind of just draw like a dotted line up here. Because there's nowhere lower than this point, like this graph doesn't go lower. It goes lower over here, but this is outside of that interval, so obviously it's not going to work. The absolute maximum is not going to occur at an endpoint. It's going to occur up here, somewhere up here. This is our absolute maximum. So what really this just tells us that there exists an absolute min and max. So really that's all that tells us. So yeah, these are the 4 key theorems that you're going to have to know. for AP Calculus. And yeah, definitely do some practice problems. I hope I helped you understand what each of them mean. I'm sure you've seen them before because, again, the point of this is to review, not to teach you. But yeah, so I hope you guys have a solid understanding of these theorems. And yeah, let's move on to the next thing we're talking about. Okay, so I did take up a lot more time than I thought I would with those 4 key theorems. So I'm probably going to have to split this video up into 2 parts, but I did want to talk about one more thing to wrap this video up, and it's going to be pretty quick. It's really on just the first and second derivative tests, and they should make sense. At least the first derivative test should make some sense, since you've already kind of dealt with it in disguise, I guess. Basically what it is the process is to find where your function is increasing or decreasing. And if you already know that, then you're good. Basically what you do is you take the derivative of your function, right? So if this is our function f, then you're going to want to find f prime of x. So first, so I guess the first step is find f prime of x. Oops. Hold on. Whoa. You just want to find f prime of x. Okay. And then your second step is to set that equal to 0. So you're going to say f prime of x equals 0. And then from there, and actually let me explain that. So you're setting your derivative equal to 0, and so that means your slope is 0. So that occurs on this graph, that occurs here and here. I don't see any other places where the derivative is 0. It could equal 0 some other parts of this graph, but from what I see, it's right here and here, okay? So over here, your derivative is, okay, the reason why we're doing this is because we want to see, like, is it going to be increasing or decreasing on either side of that? Actually, I don't need to write down this process, I can just explain it. But yeah, basically, yeah, you're trying to find where your derivative is increasing or decreasing. So what you do is you find where it's equal to 0, because that's pretty easy to do. You just take your derivative, set it equal to 0, and then find all those x values that satisfy that. There could be 1, there could be 10, there could be 0, I don't know. But basically, you're going to put all those on like a sort of sign chart. I'm sure your teachers probably showed you a way of doing that. I don't really want to show it to you because there are a lot of different ways to do it, and I don't want to confuse you. But basically, you test whether your function is, whether your derivative is increasing to the left and right of those intervals. So here it's going to be increasing, obviously. You can just see that your function is increasing. Here it's decreasing, and here it's increasing again. But maybe we could have done something to where instead of increasing over here, it starts decreasing again. So even though our slope was 0 here, we were decreasing here and here on both sides. So just because your derivative is equal to 0 doesn't mean that you're going to switch from going increasing to decreasing or the other way around. So you have to be careful of that. You have to check whether your derivative is positive or negative on either side. And just so you know, your f increasing, it means the same thing as f prime positive, right? Basically, to be increasing like increasing is basically just a rate of change. So the derivative is also a rate of change. So it means the same thing. But yeah, so you always have to check, and yeah, that's basically what you're gonna do. And you can also use that information to find local maxima and minima, all that kind of stuff. Your second derivative test should be kind of new. Basically all it is it's talking about stuff like this. And actually I can do another one here. Yeah, I'll just do another one, two things on the same graph, I guess. It's okay. Basically, if you notice, if you have a derivative, actually I don't want to do it on the same graph because that's confusing. Hold on. Let me just do it on 2 separate graphs. Actually, let me just focus on this first one up here. Sorry about that. Basically, here if you notice, we have local minimum, I guess, kind of here-ish, right? Basically, you can notice that your f prime at that point, so I'll call this point P, right? P for point, f prime of P is equal to 0. The derivative is 0, right? But f double prime of P, what is it? Well, I mean, it's upward opening, it's concave up, so it's going to be positive, so it's going to be greater than 0. If you have these two conditions, you have, so P, so actually if you meet these two, so it's like another one of those if-then statements, then P is a local minimum. And that's it. I mean, you can really just test it out for anything, but it should kind of make sense to you. Basically, if you kind of just look at it, I mean, it makes sense. It's hard to explain it, but this is always going to be true. If your derivative is 0 and you have a concave up, you're always going to be at that lowest point, because that's how concave up graphs work. And again, vice versa works with the local minimum. So if or local maximum, I guess it turns out to be here. This is our point. I'll call this Q. So we have f prime of Q is equal to 0, and f double prime of Q, well, it's concave down, so it's the second derivative is less than 0, so then we have that Q is a local maximum. And I don't want you to get those two confused, because you might be like, oh, this is positive, so it's a local maximum. No. Positive with minimum. And just draw the picture. Draw the picture whenever you're on the exam, on any tests or homework assignment, whatever. Draw a picture. It's super easy to draw, and you can see very clearly for yourself. Anyway, that's just what I wanted to show you guys. I'll talk about a couple more things in the next video. Thank you all for watching, and I will see you then. Bye, guys.